All right, everyday statistics. Here is your lesson 5.3. We're going to talk about binomial random variables. We're going to do this stuff today. It's going to be awesome or something. All right, so when we're looking at binomial random variables, we need to check to see if they are indeed binomial. And the way that we do that is by checking our bins, is what I like to call it, right? So before we can do binomial calculations, which is what we're going to learn to do in our calculators, we have to check to see that it is indeed a binomial setting. So we got to check, is it binary? So are the possible outcomes either success or failure, right? So the difference between that would be, I'm going to look at cars that go by and I'm going to say, hey, is it a Toyota, right? That would be a binomial setting, right? It either is a Toyota or it isn't, right? But if my outcome of interest was color of the car, right? Well, that's not binary because it could be red, blue, right? It's not one thing or the other, okay? I need to make sure that the trials are independent. That is, knowing the results of one doesn't change the outcome of another. I need to know that the fixed number of trials is the trials is fixed, right? That there's not varying number of trials, and that there's the same probability of success for each trial. So we'll go through an example where we check bins here in a moment. So a binomial random variable is a lot like our discrete random variable, right? We'll call it x, and it's the number of successes for some binomial set. So we can calculate probabilities for this. This is the formula. You don't need to know it for our purposes. We're going to have the calculator. We're going to use technology to do this for us. So we won't talk about the binomial distribution, right? It is all of the probabilities for each possible variable, right? So number of children with type O blood. If they go ahead and take, so we have a fixed number of trials, and so they looked at 5 children. We'll get the probability that 0 have type O blood, which is 0.23730, right? Probability that 1 of them, 2 of them, 3 of them, 4 of them, and 5 of them have type O blood. Okay. So that is what it looks like. We're looking at the distribution of this binomial random variable. We're going to create our own histogram here in a moment. But there's what it looks like. In fact, let's just go ahead and get to it. This is going to be a really short lesson filled with mostly an example of what you guys are going to be doing on your assignment. And again, I'm going to be using technology for that. So if you don't have a calculator handy, the app Calculator X does this for you, okay? Some of those TI-84 emulators, this particular function is a paid function. I'm trying to find the one for you that's free, all right? So let's go ahead and do this. According to New Jersey Transit, the 8 a.m. weekday train from Princeton to New York City has a 90% chance of arriving on time on a randomly selected date. Suppose this claim is true. We're going to choose 6 days at random. We're going to let x equal the number of days on which the train arrives on time. First thing we're going to do is explain why this is a binomial setting. So in order to do that, we're going to check bins. Right, so it's weird how that makes my handwriting look so much better. But anyhow, is it a binomial setting? Okay, is it binary? Right? Is it either a success or a failure? Well, yeah, either the train is late or it's on time, right? It's not like going to be kind of late or kind of on time. It's one thing or another, right? So this is true because the train is either late or on time. There are only two possible outcomes, right? All right. Independent. Do you think that the train being late yesterday changes the probability of the train being late today? No, right? So we would say, yeah, the train being late on one day of on one day does not affect it being late on another day, right? All right, so they're independent. Are there a fixed number of trials? Let's go back to the problem. We're going to choose 60 as at random, right? So yeah, there are a fixed number of trials. There are 6 trials. In your assignment, the first question is going to ask you to do this. Each one of these is worth a point on the question, right? The question's worth 4 points. Make sure you check every single one of these, and you have to explain it. It's a little bit long. But, is the probability of success the same for each trial? Well, it says no. It says that it has a 90% chance of arriving on time any given day, right? So then that means that on day 1 it's 90%, on day 2 it's 90%, on day 3 it's 90%. So this has been verified. So the probability of success is 0.9 for all days, right? It's the same no matter what. All right, we checked our bins. We did it. That was number 1. Oh, I just did it. I just did it one quick formula. Yeah. Um, let's calculate and interpret the probability that x is 4. Okay? Probability that x is 4. So, this is what we're going to do. I'm going to calculate this in my handy dandy calculator. So we're going to do this with our calculator. So we're going to use that app that I told you about. This is what you're going to put in. Binomial PDF. Right? And actually our calculator put it out for you. So if you have your TIE core calculator, do it like this, and I'll show you how to enter it into any other calculator that you want to have. So I'm going to hit second bars. Actually, let's write that down here. So second bars, and then we're going to choose Binomial PDF. You'll have to scroll down a little bit to get there. Binomial PDF. And it's going to ask us. So in this case, there are 6 trials, right? Because it was 6 days, yeah? The probability of success on each day is 0.9. And we're looking for x equals 4. I'll go ahead and poste. And that's what it comes up as. So now, if you don't have that screen that comes up on your calculator, you're going to have to actually enter this, hit enter, and then it'll calculate it for you. Let's write all that stuff. So for this one, you'll hit binomial PDF, and then you'll follow the prompts. If you don't have prompts, then you're going to hit binomial PDF. You're going to put 6, comma, 0.9, comma, 4. Either way, you're going to get a probability of 0.098 for rounding it down. So that is the probability. So let's talk about this in context. This is the probability that the train is on time for 4 out of 6 days, okay? Awesome. We did number 2. Now let's do number 3. Ooh, we need to make a histogram of the probability distribution of x. This is going to take a minute. Then we're going to describe its shape. It's actually going to take a while. First, we need to write out the probability distribution of x. And then we need to make a histogram. So here we go. Our possible values for x are 0, right? That's the probability that it's on time 0 days. 1, 2, 3, 4, 5, and 6. Probably not going to have room because I think we're going to have some big decimals here. But we'll see what happens. All right, so this is x. This is the probability of x, right? When we're making a probability distribution. Awesome. Now we got to calculate all these probabilities, yeah? Well, let's do it. I'm going to go to my calculator, and I'm going to actually go up and copy this. We looked at the probability that x is 4. Let's look at the probability that x is 0, right? That the train is on time 0. And that says 1e to the negative 6, which is, right, if we're, right, that is 0 0.1, 2, 3, 4, 5, right? Okay. So 0.1. 0.1, 2, 3, 4, 5, 6. Cool. Now let's look at the probability that x is 1. All you gotta do is go up here and copy this in here and put in a 1 instead of a 0. And I get 5.4 times 10 to the negative 5th power. So we'll write 0.1, 2, 3, 4, 5. There we go. What's the probability that it's on time? Only 2 of the days. So I'll hit this one. 2. Probabilities are going to get smaller. We're going to go 0.001. We can put 1, 2. Now we'll calculate the probability that x is 3. 0.015 approximately. And now, as we're going through, right, we're seeing that these probabilities are getting bigger and bigger, and it makes sense, right? If there's a 90% chance that the train's on time on any given day, then you would imagine that the chances that in 6 days it's not on time once should be really low, right? Makes sense, yeah, right? And the probability that it's on time, 5 or 6 days should be pretty high. So let's continue looking at these probabilities. We have the probability that x is 4, right? We already did it. It's over yonder, 0.098. All right. Now we just need 5. 0.354. Let's see. And then 6. Point 5, 3. Okay, let's draw a histogram. This is going to be a really weird one, right? Because we've got that really, 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 really low probability. Let's go 1, 2, 3, 4, 5, so it doesn't look super weird. 1, 2, 0.3, 0.4, 0.5. Remember, this is probability. And this one is going to be days on time. 0, 1, 2, 3, 4, 5, 6. And now it's time to fill it in, right? The probability that x is 0 is, I don't even know where to put this line, you know? And this one is like basically the same, right? The probability that x is 2 gets a little bigger. Now we're at 0.01. 0.09, that's better. For 4. For 5, we're at 0.35. And for 6, 531. Looking at my drawing. Hey, let's describe the shape of this. This distribution is skewed to the left. Well, there it is, y'all. You guys are going to have to do this on your own here in a little bit. Thanks for watching. Don't forget to smash that like button. Just kidding. I don't really care. But I hope you're having a great day. And if you're not, hope it gets a lot better.